Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course States of Matter, and I hope you are enjoying this course with me. Today we begin with lecture 28 from the course, but make sure you watch the previous ones before viewing this one. So till now we have had a detailed discussion on the ideal gas behavior, but then in the last lecture we started the discussion on the real gases. And we all now know that all gases, they are real gases. So in case you've not watched the previous lecture, please do watch the previous lecture before viewing this one, because this is going to be essentially a continuation of our previous lecture discussion, right? And what we have learned is that all gases, they are real gases. The real gases, they do uh, obey the gas laws. They do obey the general gas equation PV equal to nRT under certain conditions of temperature and pressure, but at other conditions of temperature and pressure they may not be following the ideal gas behavior. What we learned was that when the temperature is going to be high, the pressure is going to be low. Generally all the gases, they will obey the gas laws, but when the pressure is going to be high, the temperature is going to be low, we will be seeing a marked deviation of the gases from the ideal gas behavior. We have seen the plots related to that in the last lecture, right? So please, if you have missed the last lecture, please do watch the lecture before continuing further, because you will not be able to understand certain things much clearly if you have not watched the previous lecture. So in this lecture, what we will be doing is we will just be having a recap of what we have talked in the last lecture related to the causes for the deviation from the ideal behavior, and then we will be developing a understanding on the van der Waals equation for real gases. We have an equation now for the ideal gases, that is PV equal to nRT, but that is not valid for the real gases. So we will be seeing how van der Waals, the scientist, he gave us an equation for real gases, and this equation is also called as the equation of real gases for state. Fine. So in the last lecture, we learned that there were two faulty assumptions in the kinetic theory of gases which lead to a deviation from the ideal behavior for the gases, and these two faulty assumptions, they were noticed by the scientist van der Waal. So which was the first assumption? The first assumption was the volume occupied by the gas molecules themselves is negligible as compared to the total volume of the gas. Now what is the total volume of the gas? I hope you all remember that the volume that is available to the gas is the total volume of the gas. So whatever is going to be the volume of the container which is containing that gas is going to be the total volume of the gas. And what is going to be the volume of the gas molecules? Well, the volume of the gas molecules is going to be that minimum space in which we can fit these gas molecules. Okay, so now, if the pressure is going to be quite low, the gas molecules, they will be widely separated from each other. The intermolecular spaces, they are going to be much large, and the volume of the gas is going to be very large. Fine. So if the volume of the gas is very large, we can say that the volume occupied by the gas molecules can be neglected. For example, in a figure of 10,000.01, you can say that the value is approximately 10,000. You have just neglected that 0.01. But if the value is 1.01, you cannot neglect that 0.01. That is important. Fine. Similarly over here, if the gas is in a big container, we can say that we can just ignore the volume of the gas molecules. But if the container volume is quite low, right, at that condition, we cannot ignore the volume of the gas molecules. So when the pressure is going to be high, the gas molecules, they will come close to one another. The intermolecular spaces, they are going to be less, and the total volume of the gas is going to be less. And when the total volume of the gas is less, we cannot ignore the volume of the gas molecules, because the volume of the gas molecules is going to remain the same. the volume over here of at a low pressure, volume of the gas was high. At high pressure, the volume of the gas is less. So here at low pressure, we have ignored the volume of the gas molecules. At high pressure, we cannot ignore the volume of the gas molecules, right? So therefore, this assumption becomes faulty. Another thing which you learned in the last lecture was that when the pressure is going to be high, the volume of the real gas is going to be greater than that of the ideal gas, because the molecules, they are close to one another, repulsive forces, they are going to be much higher, right? So if we measure the volume of an ideal gas by the PV equal to nRT equation and the volume of the real gas experimentally, what we find is that the volume of the real gas is going to be greater than the volume of the ideal gas. The other assumption which is going to be faulty is that the molecules of gas exert no appreciable attraction upon each other. Again, if the pressure is low, the temperature is high, the molecules, they are far away from each other. At that case, we can say that the gas molecules, they have no attraction for each other or negligible attraction for each other. But if in actual real life there would have been no attractive forces, we would not have been able to liquefy a gas. How do we liquefy a gas? Well, we compress the gas molecules, bring them close to one another so that the attractive forces among them increase, and when they increase to a certain level, well, the gas gets converted into a liquid. Right? So a gas liquefying shows that there were some attractive forces which became dominant at certain temperature pressure conditions to liquefy a gas. Right? At low temperature and high pressure, the volume decreases and the molecules, they come closer, making the attractive forces appreciable, and at this time we cannot neglect those attractive forces. Fine. Now this is also varied by one very important experiment of ours, a daily life experiment also, that when a gas is made to expand, the gases cool. Okay, I will go from the other way around. That when we are expanding a gas, what happens is we see that the temperature of the gas has come down. Why has the temperature come down? The temperature is proportional to the kinetic energy. If the temperature has come down, this means that the kinetic energy of the gas molecules has fallen down, but the total energy has to be conserved. So there must be somewhere that this energy has been used so that the kinetic energy has come down. Well, this energy has been used in overcoming the forces of attraction of the gas molecules. Had there been no attractive forces, the gas would have expanded without the lowering down of temperature. The lowering down of temperature, the gas cooling, shows that there are forces of attraction between the gas molecules, and to overcome these forces, some energy had to be spent, and there is a compensation of the kinetic energy. The kinetic energy has fallen, the temperature has fallen so as to make the gas expand. I hope this is clear why a gas is cooling down when it is allowed to expand. Okay, I hope it is clear. Now that you have a clear understanding of the faulty assumptions of the kinetic gas theory, let us move on and understand how van der Waal he tried to correct for the deviations that he saw for the real gases and then ultimately reach up to the derivation for these real gases. Fine. And when we are going to see the corrections that he did for the deviations, there are going to be two types of corrections. One is going to be for the intermolecular forces of attraction that we saw that the kinetic gas theory did not take into consideration. And when it is going to be a correction for the intermolecular forces, it is going to be a correction in the pressure term for the gas equation PV equal to nRT. Why it is going to be in the pressure term, you will be just now understanding. But just remember, the first correction will be for pressure, and pressure for counting for the intermolecular forces of attraction. And the second is going to be a volume correction for the volume of the gas molecules which was not counted for in the kinetic theory. So let us first talk about the pressure correction. And here again, remember what happens at a low pressure and a high pressure. When we are talking about the intermolecular forces, at a low pressure, their intermolecular forces are going to be negligible because the gas molecules, they are far away from each other. But at a high pressure, the molecules, they are close to one another. And when they are close to one another, they are going to experience the intermolecular forces of attraction. Fine. Now what happens is, let me help you first of all with the uh, a diagram over here, and then we will be putting up everything in writing so that you can make your notes, and when you are revising you do not face any difficulty. Fine. So here we have a container. In this container there is a gas molecule. Let us assume in the center of the container. Fine. And this is going to be surrounded by various other gas molecules. Because the pressure is high and the molecules, they are close to one another, and they are experiencing what? They are experiencing attractive forces. So this molecule is going to get attracted towards this molecule, towards this molecule, towards this as well as this, and as well as this. So it is being attracted by molecules all around it, and hence the net attractive force on this molecule is going to be zero. But when we come close to the wall of the container, when their molecule is just about to strike the wall of the container, what do we see? This molecule is moving towards the wall of the container with some velocity. Therefore, it is going to strike the wall of the container with some force, and that force per unit area is what we know as the pressure exerted by the gas. Fine. So now let us look at this molecule. This molecule is surrounded on by other molecules towards the center of the container. Right? In between the molecule and the wall there is no molecule, but towards the center there are molecules, and now it is going to get attracted towards these molecules as well. Fine. What is happening? This molecule is moving in this direction, but it is being pulled back by the other molecules backward towards the center of the container. So what will happen when it is being pulled back? Well, its velocity is going to decrease, right? You are trying to run forward, but you are being pulled back by some of your friends. What will happen? You will not be able to run with that speed. So similarly, this gas molecule velocity will decrease, and therefore the force with which it will strike the container is going to decrease, and therefore the pressure it is going to exert on the wall of the container, that is going to decrease. Fine. So what we will be seeing is that the pressure of the real gas is going to be less than that of the ideal gas because of this inward attractive force experienced by the gas molecules just striking the wall of the container. Right? So let me just put this back into words so that we can revise and remember everything. So we know that the molecules, they are striking the wall of the container, but now they are not able to strike the wall of the container with full impact. Why not with full impact? Because these are dragged back by the other molecules due to the molecular attractive forces. And hence this is going to affect the pressure exerted by the molecules on the wall of the container. The pressure is going to decrease. Fine, I hope this is clear. Now, one thing that you have to remember over here is that the inward attractive force on the molecule about to strike the wall of the container is going to be proportional to the number of molecules or number of moles per unit volume, right? More is going to be the number of molecules per unit volume. More is going to be this inward attractive force. Also, what we can say is that the number of molecules striking the wall of the container at any instant is also going to be proportional to this number of moles, right? So, the number of collisions is going to be directly proportional to N by V. So again, this is going to be responsible for the inward attractive force. More molecules are reaching the wall of the container and more molecules are being pulled back by the attractive forces, right? I hope this is clear why we have multiplied this 2 times. Just let me rub this out. So the inward attractive force is going to depend upon the number of moles per unit volume into the number of moles per unit volume. Why? It is because first what we are having is that the inward attractive force is dependent upon the density of the gas. More is going to be the density of the gas, more is going to be the inward attractive force. Plus it is going to be also dependent again on the density of the gas for another reason, that it is going to increase the number of collisions per unit volume. Fine, I hope this is clear. So the pressure decrease or the pressure defect that we will be seeing is going to be proportional to n square by v square, and if we remove the proportionality constant, what we will be getting is that the pressure defect is going to be equal to a n square by v square, and a is a constant which van der Waal has used to express a intermolecular forces of attraction. Fine. So what we now have is that the pressure exerted by a gas is lower than the pressure exerted by the ideal gas, and the P ideal is going to be equal to P real plus A n square V square. This P real is the experimental value or the observed pressure, and A n square by V square is going to be the correction term. Once we have corrected the pressure which we had observed, we will be just adding these two up, and what we will be getting is P ideal. I hope this is clear. Pressure of an ideal gas is greater than the pressure of a real gas or the experimental values that we have observed. Why? Because of this correction term that was required for the intermolecular forces. A being the constant that van der Waal used for the intermolecular forces of attraction, multiplied by the number of molecules square or the number of moles square divided by volume square. Fine. So this is a correction that we have done now in the pressure. Now let us see how we are going to correct the volume. Now as far as the volume correction is concerned, van der Waal, he noticed that the actual compressibility volume of a gas is less than the volume of the container because of the volume occupied by the gas molecules. What this means is that if we have this container over here, according to the kinetic theory of gases, the gas molecules, they are point masses. They do not have a volume of their own. Fine. So when we will try to compress a gas, we will try to pull a piston downwards, we should be able to reach the bottom of the container. Okay, so we are able to compress the gas up till the volume of the container for an ideal gas. But for a real gas, what we will be seeing is that we will not be able to compress a gas up till the volume of the container. We will be able to reach, say, at just this level. Why at this level? Because the gas molecules, they are not point masses. They do have a volume of their own. So when we will be pushing the piston downwards, it will not be able to go beyond this level because this is the volume that the gas molecules, they are occupying. Okay, they are now in close contact with another and we cannot go further. Okay, I hope this is clear. Now, what this means is that had this been a volume of a ideal gas over here, we will be getting V ideal to be 0, right? But here now for V real, it is somewhat greater than 0 because the gas molecules, they have a volume of their own. So V real is greater than V ideal. The value for the volume that you have found out experimentally is greater than the volume value that we will be getting from PV equal to nRT. So if we put the volume over here to be the volume that you will be finding for the real gas, you will have to minus something, subtract something from here to get the volume of an ideal gas, right? So this is V real or V observed minus something that you have to do over here to get the volume of an ideal gas to put into the equation PV equal to nRT. Fine, I hope this is clear. Another thing that you have studied while we were talking about the real gas and ideal gas behavior in the last lecture was that if we have this PV curve over here, the curve for an ideal gas was this way and for a real gas it was this way. So at a high pressure what you saw was that V real is greater than V ideal because of the repulsive forces of attraction. Okay, so what is happening over here is that the repulsive forces they also become significant when the pressure is going to be high. The repulsive forces, they are short range interactions and they are significant when the molecules they are almost in contact. This is a situation at high pressure, and the repulsive forces cause the molecules to behave as small impenetrable spheres. Because of the repulsive forces, the molecules they cannot be collapsed. Okay, you just cannot put more pressure and collapse these molecules. The repulsive forces do not allow them to behave so. Okay, so they are solid now spheres which cannot be collapsed. They will be occupying a volume, and the volume that they occupy is called as excluded volume. This is also called as co-volume. Okay, I'll just rub this out so that I can write out the remaining lines. So van der Waal, he suggested to take the volume for n moles of the gas as V minus NB. Okay, this B is the uh, constant which is known as the co-volume or excluded volume. This is for one molecule, and when it is going to be for n moles, we will be doing this as V minus NB, and this is going to depend upon the nature of the gas. Why it will depend upon the nature of the gas? Because if the molecular size is going to be more, when the value of B will be more, right? Because they will be occupying now the gas molecules, when they will be bigger in size, they will be occupying a greater volume. When the molecular size is going to be less, they will be occupying a lesser volume. So the value of B will be less. Co-volume, now also remember that this is not the actual volume occupied by the molecules. It is found to be somewhat 4 times greater than the volume of the gas molecules. There will be some spaces between the gas molecules also which we will not be able to utilize. I hope you can understand that if you just pack the molecules also, okay, when we will be just packing them close to each other also, what we will be seeing is that there are going to be still some empty spaces in between. However close we may pack certain things, there are going to be some empty spaces which will not be able to utilize. So the co-volume or the excluded volume is going to be 4 times the actual volume occupied by the gas molecules. This is not going to be the actual volume occupied by the gas molecules. Remember this thing, this is very important. So now that the pressure and volume correction they were done, Van der Waal he gave the equation of state for the real gases, and now the equation is P plus A n square by V square into V minus NB. This is equal to nRT. This is the corrected pressure and this is the corrected volume that we have now. If that is going to be just 1 mole of a gas, you can write the equation as P plus A by V square into V minus P. This will be equal to RT. Fine. Here you have to remember that A and B, they are known as the van der Waal constants, and their value will depend upon the characteristic of a gas. And the value of A, which is a measure of magnitude of the intermolecular attractive forces within a gas, please do remember this is going to be independent of temperature and pressure. This will be the inherent characteristic of the gas. The equation now that we have for the real gases, you will be seeing that this is obeyed by all gases up to quite high pressure with a reasonable accuracy. And now finally we can conclude over here from this discussion that the real gases, they will be showing ideal behavior when the conditions of temperature and pressure are such that the intermolecular forces are practically negligible, and this generally happens when the pressure this approaches zero. It is a very low pressure. So next we talk about the units and the significance of the van der Waal constants, and please be very attentive, learn this very well because these are frequently asked in the examination. So first of all we have the units of A. So we now know that A n square by V square is what term? This is a correction of the pressure. So the units of whole this term has to be equal to that of pressure. So let us take these to the other side to get the units of A. So we have A being equal to PV square by N square. P is what? This is pressure, V is volume, and N is the moles of the gas, right? So for the units, if we are supposed to write the units of A in the SI notation, what we will be getting is pressure to be equal to Pascal, volume to be equal to meter cube, and mole is the SI unit for the amount of gas. So we will be getting A to be equal to Pascal meter 6 mole minus 2. Fine. But if there are different units for pressure and volume, you will be getting different units of A. For example, if we express the pressure in atmosphere, volume in decimeter cube, what you will be getting, the units of A will be equal to atmosphere decimeter 6 mole minus 2. So whatever are given to you as the choices in the examination, you have to just see what are those choices, and from this relationship you should be able to reach up to the correct choice. This is also the correct units of A. These are also the correct units of A. It is only dependent upon the units of pressure and volume. Fine. I hope this is clear. Next we come up to the significance of A. So we now know that this A is related to the intermolecular attractive forces. And now if the intermolecular forces are strong, or that means that the value of A is going to be more, or if the value of A is more, this gives us an understanding that the intermolecular forces of attraction are going to be more. And when these are more, please do understand that the gas molecules, they can come closer to one another because of the strong forces. And when they are going to come quite close to one another, well, a gas can be converted into a liquid. So what this means is that gas which is going to have a high A will be able to liquefy easily. Okay, so if in your examination there are certain questions in such a way asked to you that this various values for the gases, A is given to you and you are asked which of the gas will liquefy easily, then you have to choose a higher value of A for the gas to be liquefying more easily. Okay, next we come up to the units of B. So for B, now we know that NB is going to be a correction for the volume. So the units of NB have to be the units of volume. Fine. So it is the incompressible volume per mole of a gas. The volume of the gas which we were not able to compress because it was the volume of the gas molecules per mole of the gas is the units of B. And it is going to have the units as that of volume. So if the volume is going to be expressed in meter cube, so the units of B is going to be meter cube mole inverse, or if it is expressed in decimeter, then it is going to be decimeter cube per mole. Okay, I hope this is clear. Next we move on to the significance of B. Now B, you all know this is because of the incompressible volume of the gas molecules. So the value of B is going to be related to the size of the molecule. larger is the size of the molecule, larger is going to be the value of B. So from your periodic classification, if I ask you which of the two fluorine or chlorine gas molecules is going to be larger in size. Okay, so fluorine is going to be smaller in size than chlorine. So this means that the value of B is going to be larger for chlorine than for fluorine. Okay, so this is going to be the importance. If the value of B is going to be great, the size of the molecule that means was greater, or if we know that the size of the molecule is great, then we can predict the value of P. More is going to be the value of P for a greater size of the molecule. Next, we understand the behavior of the real gases as explained by the van der Waals equation. And trust me, this is going to be a recap of the last lecture as well as this lecture. What all we have learned till now, we are going to sum up all now. Fine. So what we have learned is that at a low pressure, the gas molecules, they are far away from each other. When they're far away from each other, we can say that the volume of the gas is going to be much high as compared to the volume of the gas molecules. So we can neglect B, the volume of the gas molecules in comparison to the V. Fine. So we can neglect this, and also we know that the intermolecular forces are going to be negligible. So we can also neglect A by V square, which is going to be very small in comparison to P. So the van der Waals equation, this will simply reduce to PV equal to RT for 1 mole of a gas. Okay, and therefore this means is that at a very low pressure, the gases, they do obey the ideal gas equation. Next, we move on to a moderate pressure. Now, at a moderate pressure, what means is that from a low pressure, we have started increasing the pressure slightly. When we are increasing the pressure, this means that the volume of the gas is decreasing. Fine, the volume is decreasing, but still this is not a very sufficiently high pressure. So this means is that the volume is still large, and when the volume is still large, we can neglect B in comparison to V. But as the molecules, they are coming closer to one another, the intermolecular forces, they are appreciable. The value of A by V square is increasing, and this we will not be able to neglect in comparison to P. Okay, so the van der Waals equation, this becomes P plus A by V square into V equal to RT. If you solve this further, what you will be getting is that PV plus A by V is going to be equal to RT, or PV by RT plus A by VRT, this is going to be equal to 1. Now, if you remember the previous lecture, what we said was that PV by RT is equal to what? This is equal to Z, the compressibility factor. So let us replace this by Z. What you will be getting is Z going to be equal to 1 minus A by VRT. And because this is something being subtracted from 1, at a moderate pressure, what are we getting? Z is less than 1, right? This is a negative deviation that we are seeing. Okay, this is not ideal gas behavior. Another thing now, what you can see is that if we increase pressure in this range, right, if we are going to increase pressure, the volume is going to decrease, and as a result, this whole term A by VRT is going to increase. So what we will be seeing is that the value of Z will decrease with increase in pressure till it reaches a certain minima, and then it will start increasing. That is what we have been studying in the previous lecture as well. Now what happens at a high pressure? At a high pressure, the volume of the gas is going to be less now, right? And when it is going to be less, the volume of the gas molecules, this cannot be neglected. So B term cannot be neglected in comparison to V. Similarly, when the gas molecules, they are going to be close to one another, the value of A by N square, this is also going to be quite large. But what you have to remember over here is that when this value is increasing, the value of pressure is also increased quite a bit. Fine. And when this is a high P, we and still neglect this term. This is going to be quite small in comparison to the higher pressure that we will be having for the gas. So we will be neglecting it. Fine. So the equation now becomes P into V minus B equal to RT for 1 mole of a gas, and if it is going to be N moles, it is going to be P into V minus NB equal to nRT. Fine. If you solve this further, what you will be getting is PV minus PB equal to RT. Divide this throughout by RT. You will be getting PV by RT minus PB by RT equal to 1. And PV by RT is the compressibility factor Z. So just put the value here as Z. Z is equal to 1 plus PB by RT. So something is being added into this one at a high pressure, and Z is going to be therefore always greater than 1 at a high pressure. This is what you have studied. This is what we have as a positive deviation. Also, what you can see here is then when we are going to increase the pressure value further, the value of PB by RT will keep on increasing, and the value of Z will keep on increasing greater than 1. Fine, I hope this is clear. So the gases, they obey the ideal gas equation only at low pressure. At a moderate pressure, it is going to be Z less than 1. It is going to be a negative deviation. The value will keep on decreasing up till a certain minima, then it will start increasing, and then it will cross again the ideal line, and then it will move for Z greater than 1, and it will keep on increasing as we increase the pressure further. Now what happens at a high temperature? At a high temperature, at any value of P, the value of V increases because the gas molecules, they are going to move at a faster speed. They will be going away from each other. Okay, therefore the volume of the gas is going to be much greater than the volume of the gas molecules, and therefore we can neglect B in comparison to the V. A by V square is going to be negligibly small, and this can be again neglected in comparison to P. And therefore the van der Waals equation, this will become PV equal to RT, or for N moles it will become PV equal to nRT. Next, let us talk about the exceptional behavior of hydrogen and helium, which we studied in the last lecture. For hydrogen and helium, we studied that the value of Z is always greater than 1. Why? Well, hydrogen and helium, they have small masses, and because of this, they have extremely small intermolecular forces of attraction even at high pressures. Okay, so what we will be seeing is that the value of A by V square is going to be negligible at all pressures, and therefore this can be neglected in comparison to the pressure term. And the van der Waals equation, therefore this is going to become equal to P into V minus E equal to RT at all pressures, right? If you solve this further, again you will be getting Z being equal to 1 plus PB by RT. So the value of Z is greater than 1, and also if we keep on increasing the pressure, this term will keep on increasing, the value of Z will keep on increasing. So what we see for hydrogen and helium, the value of Z is going to be always greater than 1. Now, with this understanding, I hope you can understand very well that the van der Waals equation, this is definitely quite an improvement from the ideal gas equation, because this is able to explain the deviations from the ideal behavior. In fact, it has been found to be very accurate over a wide range of temperature and pressure, but still the van der Waals equation, it has its own limitations. Let us now see what are those limitations. So the first limitation is that the van der Waals constants A and B, they are empirical constants. Their value is going to depend upon the nature of the gas. Okay, so with each different gas, the value of A and B is going to be different. Therefore, the generality of the gas equation has been lost. We cannot apply the same equation to every gas, because for every gas, the value of A and B is going to be different. Fine. Okay, the next we have is that the PVT relationship shows appreciable deviations when the pressure is too high or the temperature is too low. This is because the values of A and B, they vary with temperature and pressure. So these are two limitations of the van der Waals equation that we have. So that would be all for this lecture. And now that you have a thorough understanding of the ideal gases, the real gases, we can compress the gases at a high pressure and a low temperature. Well, we are going to start our discussion on the next lecture on the liquefaction of gases and a very important term, critical temperature. All that is going to come up in the next lecture. So please be with me for the next lecture. Also, do subscribe to the channel and also click on the bell icon so that you get the notification for the next lecture when we post it. And also, if you've liked this lecture, please do click on the like link. Thank you and have a nice day. God bless you.